Broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody, and I am here. And today is February the 15th, and I have one engineer here in Fresno, and the remaining are online. Welcome to the surveying review. I hope that everybody is studying very hard and prepare for the exam. And look to the schedule very quick to see where we stand. And let's go to the schedule here. Okay, let me open it because probably I did not. Okay, where is my, here it is, sorry. Cannot see it, but here is a brochure. Click on it. And let's go to the surveying review. Excuse me. Here it is. So today is 2:15 Saturday. Okay, this is a workshop number 3. We still have 2 to go till the end of this quarter, and after that there will be a class that will start April something, April 18, yes, April 18, and I hope that by that time, I think the second edition should be released with some updated information, updated problems, and so on. So let me open the floor for any discussion, if there is any specific discussion. Otherwise, I will start solving problems. If any of you have any question about the surveying topic in general, or topics, or any problem related to any problem from my book or from other books, I have no problem with that. If not, I will grab problems and start working on the problems that in my book, or from maybe sometimes I remember something and I try to solve it. For example, I believe there was a problem. Let me see if I can get it very quick. It is a good problem. Somebody asked me about it, and I solve it for him or her, or maybe we'll solve it here. I can't remember really. Sometimes in fact, 2 problems, and I will be glad to work it with you, and also I will send it with my solution. If you are given a problem like this, okay, as you know, mesh diagram is one of the problems that you might see on the exam, and I assume that this is, the title is not here, list. It is. Let me call this problem number 1. Okay, because the exam is a computer-based test. So from the computer, you should work the problem. Is this correct? So you don't have to have a hard copy of the problem. So I will try to make it as nice and as clean and as visible to you, and as so there is a table here. This table is given where you have excavation in cubic yard and the embankment also in cubic yard, and you have a station here, and he gave you some kind of a room for a diagram where you have cut and fill this cubic yard, and the x-axis is the station. And given the earth volume shown in the table, the first balance point on the mass hole diagram is, obviously on the exam, the CBT does not allow you to draw, or you will not be able to draw something. Okay, even with this problem as given like this, I will never think to draw it. It's time consuming, and it will not really save time for me. But I can use the given information in this table to find the answer. And some keywords here like first balance point. as you know, mass diagram is a relationship between the two variables that I talked about them before. As a reminder, it is the x-axis and the y-axis. The x-axis is station, and the y-axis or the ordinate cumulative volume. So this is 0, and this is x, or this is a station. Station 1, station 2, station 3, station 4, station, name it. And this is the volume, and they agreed that the cut will be here, which is positive, and the fill is going to be here below, and it is negative, as we solve a problem before. If you ask where is this problem, you don't have it. If somebody asks me where is the problem, unless somebody's giving me the answer, let me say that I am taking test on March 30th. Oh, Larry, okay. Vernier scale, yes, I remember that. Thank you. Okay, let me, after I finish this, I will go. Yeah, I remember you sent an email to me about the Vernier scale, and Larry had taken the exam. I wish the best to you, Larry, and to all of you. March 30th is coming. March 30th is coming. I wish you the best. And Lee, okay, you asked me about the Vernier, and I replied back to you. And even somebody sent me an email. Also, it has some kind of is saying that there are some typos in one of the problems, or maybe typos. I have the list. I didn't get a chance, I believe, or I start, but I didn't finish it. Okay. So, fill is negative and cut is positive. I believe you have access to this problem in another format, but let me talk about it, and after that we'll see. So we said that the mass diagram is a relationship, and it could be a straight line, it could be a curve. So if it's a straight line, series of straight lines like this, then maybe I will end here somewhere. This point here is very important. We call it balance point. In fact, this is the first balance point in this mass diagram. Why? Because I have cut, and after that I have fill. Cut is always a positive slope, and the fill is negative slope. And this is a high point, as we know. A high point is a change from cut to fill. So in this problem here, if I am able to establish the cut and the fill and get the ordinate, this is called the ordinate or y-axis, which is the ordinate, I can answer the question. So drawing here, I told you I will not really think for a second to have a drawing, because drawing is time consuming and so on. So in order to complete this problem, maybe I will draw something here. I'll complete the table. Okay. And I will say this here is algebraic sum. And cut, which is the excavation, is always positive. As you can see here from the drawing, this is 0 here, so this is the plus side, and this is the negative side. Embankment is fill, so I put the plus here, a plus here, a plus here, and instead of using letters, and this is minus, and this is minus, 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 minus. So if you add the 0 and 0 will give you a 0. 3,000 and this will give you plus 2,000. And if you look to this, this is a plus 500. Okay. And 15 and this is still a plus 500. And this is a plus 1,500. This and this is 0. And this is 0 minus 1,500. I'm adding just the two columns minus 2,000. Algebraic sum minus 1,000 and a minus 500 and finally a plus 500. Any question about this column, which is basically the sum, means the sum of the cut a plus fill. I am adding them together with the proper sign. Is this the algebraic sum of the cut and fill? Is this is the y-axis? No. If this is the y-axis, you will find that the 0 here is at station what? At station 5 plus 0, 0. And 5 plus 0, 0 is among the answers. If you select the answer A, you are totally wrong. You see, we cannot, the algebraic sum, you have a 0 here. This, you may consider this is a balance. No. I have to create or I have to establish another column. Do you remember the column? Is the last column is called the cumulative. Where can I put this column? Let me try to squeeze it here. This column here, I will call it cumulative. Cumulative. Cumulative means additive. What do you mean by additive? What we will do with this? I will take the first number, which is 0, I put it here. I will take this 0, I will add it to the 2,000 I have, and bring it here, will give me a plus 2,000. I will take the plus 2,000 and add it to the 500, will give me a plus 2,500. And keep doing this. This will give you this. So a plus 3,000. And the 3,000 plus this will give you a plus 4,500. I will take the 4,500 added to 0. It's still 4,500. 4,500 plus minus 1,500 will give you a plus 3,000. And a plus 3,000, I will put it here. The 2,000 will give you a plus 1,000. A plus 1,000 and minus 1,000 will give me 0.00. And 0 plus this will give you a negative 500. And from the 500 minus 2 here will give me 0.00. Do you see this column? How did we establish this column? We take the previous reading additive, and probably you did this before we do this, by the way, for speedy studies and for it's called FM, finance models for SAND. It's called cumulative. You take the previous reading, the first one, and take this and add it and so on. If from here, this is the ordinate, this is the y-axis, or as we call it, the ordinate, which is this axis here. When you put your mass diagram graphically, you establish the mass diagram graphically. So this is the station. You will put the station 0 and station 1, 2, and this is 0 and this is cut, a plus, and this is fill. minus. If you plot this mass diagram, you will find that we have a 0 balance point. Here it is. At station what? At station 8. Here it is. And this is the answer, by the way. This is the correct answer at station 8. So from the diagram, you will get the same answer, but instead of plotting the diagram, and takes time, and this is, so the first, here it is, this is the first balance point. Do you see it? Okay. So if we understand the concept of the mass diagram, I know they are coming with, every time they come up with tricky problems, new problems you never heard about it, or you never saw it before, and this is the nature of the exam. All the exams are like this, by the way. They come up with problems never exist. Okay, they are sitting and they go to Hawaii and facing the ocean and see the waves, and they start to think about problems. They are creating or innovating problems, but the concept is the concept. If we apply the concept correctly, yes, some problems are tricky, I cannot deny that. Some problems are really lengthy, I cannot deny that either. But if we understand the concept, we will be able to. If you plot it, you are very welcome to plot it. You will find that you will get the same. This is the first balance point. It does have another balance point, by the way, which is this one here. This is the second balance point. In fact, this job, because any mass diagram will tell us if the job is cut greater than fill or cut equals fill or cut less than fill. Those are the three scenarios normally exist. Okay, so this specific problem, if the project is, or this question, instead of asking what is the first balance point, they ask you, is the project this or this or this or whatever answer you will add. Obviously, I have this scenario, so the job is balanced. Balanced job. How I know that? From this column here. I start with 0 and I ended with 0. So I start here, this is a 0. And if you plot the mass diagram, you'll go up like that, come like here, and you ended here. I'm just drawing. So you start, you ended here. This is a second balance point. And this is the first balance point. You see it? And this is probably the general overall shape of the mass diagram. So we need to understand the mass diagram, and if you take this data and plot it into scale, you'll get something similar to this. But the main concern here is what station is that? And here it is, station 8. Where the cut, and because all this is cut, positive, and they start to come down, fill, until we hit 0. This station line, which is the x-axis, sometimes we call it the balance line also. Another name for it is called balance line. Balance line or station line. Okay. So this is a problem that just somebody asked me, and I believe, if I'm not mistaken, because I have tons of problems for the last 30 years, I don't know, so sometimes I forgot what I had for lunch today, but so if you ask me how many problems over the 30 years or which I can't remember. But the reason that, okay, I believe I have set of problems called 11 mass diagram problems. I don't know if you have it or not. I would be glad to send it to you. If you okay, it's called 11 mass diagram 11 mass diagram problems. I have it with solutions. I will be glad to send it to you if you don't have it. If you have it, that's good news. If not, okay, just email me info@passpa.com and I will be glad to send it to you. Okay. Before I leave this book, I will scan this and send it to you for those who attended today. Another problem, maybe, let me see if, let me get another sample book because maybe I solve it here. I don't know if not, I will make a copy very quick and we can work it together. It might be. Let me make a copy very quick. So here is another two problems. They are also considered. Problem number 2. Let me give you a few minutes to read it. Or let me zoom out. Try to get it. So, and nobody will ask you to memorize any equations, but we need to do our best to know exactly where are the equations needed for a problem like this. Here it is. Problem number 2. Problem number 1, we solved the mass diagram problem. I will scan it, send it to you, or somebody on Monday will do that. So I said an overhead sign is located at the BVI station of a crest vertical curve. The grades are 3% positive and negative 2%, with a vertical curve length of 500 feet. The BVI of the curve is at station 85 plus 00 with an elevation of 202.3. In order to provide a clearance 16 feet, the minimum elevation of the bottom of the sign is most nearly. You see that? Again, equations, they are available. So this is a crest vertical curve. This is a vertex, or the BVI, by the way, point of vertical intersection, BVI. And this is the beginning of the curve. And this is the end of the vertical curve, EVC. And this is L, as all of you know that the curve length is measured horizontally. So L, he said that it is 500 feet. And we have a sign, the BVI first of all. Let me put the information about the vertex. It is at station 85 plus 00. And the elevation here is 202.30. And somebody put a sign here at this station. Somebody passed his PE and he is happy. And he said that just passed PE. He just passed his PE exam, so big sign. We need from here to here, this is a sign. We need a vertical clearance minimum of 16 feet. So what is the elevation of the bottom of the sign? So the elevation of the bottom of the sign, this is what he's looking for. Knowing the station and the elevation of the vertex. This is a vertex here, or the BVI. Do you see the picture? Okay, during while you are studying, try to draw as much as you can. Translate as much as you can, because this will make your life easy during the exam. You don't have to draw every single problem during the exam, because by practicing during the preparation, you will be able to visualize or look. Okay, so we need the elevation to be, we need the elevation here. The grades are given, by the way. This is plus 3%, and this is minus 2%, which is G1 and G2. Do you remember G1? And this is G2. The grades are given, the entering grade and the exiting grade, and the curve length. So this station is given, which is a BVI, where the sign is. There are more than one way to solve the problem. And this is true for some problems, by the way. Some problems, there are more than one way. And always ask yourself after you solve a problem, is this the only way to solve this problem? Maybe there is another way, shortcut. Maybe there is another shortcut, faster, time saving. If you look to my book or in other surveying books, you will find this distance from here to here, it has a name. The distance between the curve and the vertex. I call it in my book D sub O, or we call it E. Actually, they call it E. So D sub O or E, we call it offset or vertical offset, at the BVI. So if you have any surveying book, including mine, I didn't invent surveying. I'm just presenting surveying. Do we have an equation for D sub O or E? You will find there is one equation. It says that it is AL divided by 800. D sub O or E. So if you plug the numbers, A is the algebraic difference, by the way. A is the algebraic difference, G2 minus G1. So A is 2 and 3 is 5, or minus, so it is 5 times 500 over 800 will give you a number. This number is, and I know you have some questions, this will give you 3.125 feet, if my math is correct. First of all, locate the equation in my book, in chapter 10, by the way. Chapter 10, at the end of chapter 10 of my textbook, you'll find this equation there. Since I know this distance from here to here is 3.25, so, and I know the total distance to be 16, that means that the remaining is what? The remaining distance between the BVI and the bottom of the sign is equal what? Is equal the difference, 16 feet minus 3.125 feet. So if I know from here to here is 3d sub O, and I know from the curve to the bottom of the sign 16, this is where the traffic will be. So the difference between them is 16 enter 3.125 minus, it is 12.875 feet. Since I know that, and I know the elevation of the BVI, so the elevation at the bottom of the sign is equal what? Is equal the elevation 202 that's given to me 0.30 plus the 12.875. So if you do that, 202.30 plus, I get 215.175 feet. And this will give me 215, the closest 1.18, and the answer is B as in boy. Any question about this? This is one way. There is another way that you can determine the elevation along the curve itself at this point using the general equation. You can use this general equation, y is equal at any distance x is equal y of the BVC plus g1x plus rx squared divided by 2, which is a general equation for vertical curves. And after that, I will add the 16 feet to it. But what I did, I calculated E, or the D sub O, and I took the difference, I add the difference to the elevation of this point. But this one is a little bit longer, a little bit. Is not the other approach, calculating the elevation along the point, or at the point along the curve, and add 16 feet to it. This is another way. But this is shorter as far as the way to solve it, and you are very welcome to solve it the other way. Will be a good test for you, or a good practice for you. Makes sense? Any question about this? It seems to me there is a question. Let me grab this question here from one of you. Where is the equation? Oh, the equation is in the book. Okay, in chapter 10. Let me see if I have it or not. In chapter 10, go to chapter 10, vertical curves, and all the way to the end, chapter 10. Let me see, probably is not there. Here it is, D sub O. D sub O is the vertical clearance at the BVI. This D sub O, or if you call it E, that's fine. Another form of it, this is G1 minus G2. This is what we call it A. We used it before also. So this is AL divided by 8. If you use it like this, the answer will be in stations. But if you say that AL divided by 800, so the answer is going to come in feet directly. It's up to you. But the equation is there. If you'd like to plug it exactly and solve it as given here, and plot the percentage, you will get the same answer. And because this is why I did not put A, which is the 5%, I didn't use the 5%. As you can see, I put here the the 5, I didn't put 5%. I dropped the percent because I have 0 here. Let me explain this. So the D sub O, Larry, sorry, is given as equation in my book, equation 10-27. Is equal G1 minus G2 times L divided by 8. So let us do it the other way. G1 minus G2, G1 is a plus 3 minus minus 2. Okay, these are percentage. And the L is 500 feet divided by 8. So this is 5%. And these two vertical lines, by the way, what does it mean, these two vertical lines? This means that we are taking the absolute value. Absolute value. We don't consider the sign. It could be G2 minus G1 to give the same answer. 5% times 500 divided by 8. So if you do this, 0.05, enter, 500 times 8 divided, you will get the same answer, 3.12 feet. But in this case, the 5% will show also 0.05, 5% times 500, which is L, divided by 8 will give you 3.125. Check it, check the math. Or you can say that D sub O is equal to the same G1 minus G2 times L divided by 800. That means that I will drop. So in this case, I will say it's just only 5. I didn't put 5%. You see, 5 times 500 divided by 800 will give you also 3.125. Is this correct? Mathematically, both of them are correct. Normally, we drop the percent. It's much better. This is equation 10-27 of my book. Make sense? Everybody got it? And you should get the same answer. It doesn't matter as long as we know what are the parameters of the equation. Okay, good problem. And when you receive it, go over it again, and you are very welcome to ask any questions when you receive my solution. But I highly recommend you to solve it the other way. This is another approach. If there is only way, no. The answer is no. You can go this. This is another approach. Another approach or another method. Yes.
I'll go over one more time to how to determine the elevation at the beginning of the curve for this problem.
Oh, you can get it easily.
Okay.
Without any calculation.
Sure.
Here it is.
It's using the grid, right?
That's it. Yeah. Here it is. Our friend is asking how can you get the elevation of the beginning of the curve. Let me remind you. Here it is. This is here it is. And here it is. So this is the vertex or the BVI, which is, it has a station of 85 plus 00 and the station 202.30. This is given. And the L is equal 500 feet. And this grade G1 is equal plus 3%. And this is G2 is equal negative 2%. And this is the beginning of the vertical curve, and this is the end of the vertical curve, or if you like, VBC, vertical point of curvature, and this is VBT. These are other names. We need to be familiar, and I mention all this also in my books. And how can I get this elevation here? Okay, the easiest way is, I know the elevation here. So it is 202.30. I will say minus. From here to here is half of the curve length, which is 2.5 station. 2.5 times the grade, which is 3. So if you do this, you will get 2.5, which is half of the curve in station 3, and 202.30 minus, I got 194.80. This is the elevation of this point. You don't have to use a percentage. And the elevation of this point here also, the end of the curve, very easy. I will use this one here. It is 2.5 enter times 2, 202.30 minus, so it is 197.30. Those are the elevations of the beginning and the end of the curve. You need the elevation here if you are going to use the general equation. Y at any distance x is equal y of the BVC plus G1x plus Rx squared divided by 2. So when you receive this problem from me on Monday, please go over it again and try to solve it the other option or the other way and see if you are getting with the same answer or not. If not, please let me know and I will be glad to talk about it. Okay, make sense? You are very welcome. The problem according to problem number 3, let me give you a few seconds to read it. And there is a problem similar to this, by the way, all these problems are additional problems from other sources, but there are similar problems into my books. I don't like to say verbatim. This is almost the same, almost. I can't remember as I said that. Forgive me as getting old and Alzheimer's, so I'm getting old. So read the problem and tell me what do you think. Okay. I will make another comment or additional comment related to this problem, which I call it problem number 2, before I go to problem number 3. But let me just clear this so when they make a copy for you or scan it and send it to you, to be nice and clean. But the copy machine made some kind of dark spots here. Okay, just make another comment related to this problem, because for vertical curves, and let me use a vertical curve, the one we're referring to, this distance from here to here, as I told you, in my book, I use D sub O, or as I told you, AASHTO, they are using E. E like external distance. And we know the equation that we just saw it here, or we just did it here. So this is E, and this is also E. This we call it vertical offset at, this we call it vertical offset at the vertex slash VPI or BVI. The 3 names, by the way, for this. This point here is a vertex, or this, where the 2 tangents are intersect, vertex, or BVI slash VPI, or BVI, whatever name you like. All of them are available in surveying books. But there is another vertical offset. What's a vertical offset? This one here is a specific one, but this is also a vertical offset, but not at the vertex. This is another vertical offset. All these are, we call them vertical offsets. So this is a vertical offset. This is a vertical, at different stations, obviously. This vertical offset, any one of them is called Rx squared divided by 2. I need you to know that. This is a vertical offset. Rx squared divided by 2. And this is also given in my box, because this is something important. And specifically, this equation is given, by the way, as equation 10-30, by the way, in my book. 10-30. You go to chapter 10, you will find the equation. It has a number 10-30, which is Rx squared divided by 2, where R is a rate of gradient change per station, and X is the distance measured from the beginning of the curve, as usual, and 2 is 2, okay? So we need to be aware of that. Just a very quick clarification about, because there are 2 vertical offsets. There is one unique vertical offset is located at the vertex, and we have series, or we have many vertical offsets. It depends on the station or the location. Problem number 3. Problem number 3 is a horizontal curve. This is vertical curve. This is a horizontal curve. This is a PC, point of curvature. This is PT, point of tangency, or this we call it end of curve slash beginning of curve, PC. Beginning of the curve, end of the curve, point of curvature, and point of tangency. And this is a PI, point of intersection. And this is called delta. Some books, they call it I call it delta also. This is deflection angle. And the deflection angle, by the way, it is also equal to the central angle. This is the center of the. So this is R, and this is also delta. But here we call it central angle. And this is the radius. So he's saying that an existing highway has a historic site located at the PT. Here it is, a historic site. So excuse me. The BI is located at station 80 plus 00. External angle 65. This angle here. Deflection angle or external angle is acceptable, both of them. So external angle or deflection angle. Deflection angle is the most commonly used. External angle. The radius is given to be 1200 feet. The curve must be relocated by moving the PI to station 78 plus 00. Here it is 80. So it has to move here. The PI, the new station here is 78 plus 00. The external angle and the BC remain the same. The radius of the new curve is. So because of this historic site, they decided to shift the curve. So if we bring a straight edge or something like that, and let us do it. So here it is. The angle is still the same. So this is going to move parallel this way. From here, here it is. This is a new forward tangent. Because there are two tangents. This is called back tangent. And this one here is called forward tangent. Forward. So we are moving the forward tangent inward 200 feet, which is the difference between this and this. Are you following me? So he's saying that the external angle BC, the external angle and the BC will remain the same. So what do you think? Is the curve, first of all, sometimes the logic or the original radius is 1200. And here we have 4 answers. It started with 263, 314, 866, or 1200. Do you think the answer D, which is the same as the original radius? Right now, after we did that, we are going to have, let me draw a curve for you. Bring something so I can show you the new curve and you can because sometimes a picture. So right now I'm going to draw a curve tangent to the two tangents, the old one and the new one. Here it is, the green one. See, this is a new curve. After we shifted the forward tangent, the 200 feet required to stay away, all this to stay away from the historic site here. Because we have lanes and we have all these things. So he is saying that what will be the new radius? Is the radius going to stay the same? This is the first question that, excuse me. Is the radius, so is answer D acceptable answer? Or a logic answer? No. So again, equations available everywhere in all surveying books. The biggest concern is, or the biggest issue is, what equation should be used and what equation is going to give me the answer quickly. So the original curve, it has radius, so it has a tangent. Tangent is equal what? Is equal r tan delta over 2. This is one of the equations that I believe that tangent is from here to here. This from here to here. This I will call it T1. Let me T1, and this is R1. So T1 is equal to 1200 tangent. Delta is given to be 65 degrees over 2. If I do this simple math, you can help me with that very quick. Always bring your calculator. I need you to be participating. I got 764.48 feet. This is what I got. This is a T1. But after I shifted, or after we moved the forward tangent, this is T2. From here to here is T2. So T2 is equal T1 minus 200 feet. Do you agree with me? So basically is equal to the 764.48 minus 200 feet. This will give me the new tangent. Okay, which is the difference between these two. It is 564.48 feet. This is the new tangent length to T. But this is also equal what? Is equal R2 tan delta over 2. Did we change delta now? So in this case, R2 is equal T2 divided by tangent delta over 2. So it is equal to the 564.48 divided by 10, 65 degrees divided by 2. Let us do it and see if we're getting one of these three answers, sorry, because already we scratch one of them because it does not make any sense. So in this case, 65 enter 0.5 and the 10 and the inverse, and I would say that 564.48, I got 886.0561. This is what I got in my calculator if I did everything right. So I can round this to be 886 feet. And this my answer C. If you agree with me, that's good news. If you disagree with me, it's still good news, because at least you can figure out what mistake I did or what is the disagreement, because makes sense. You need to be ready for the exam to a degree that when you read the problem, your computer, which is your brain, store the equation, and we know where are the equations, where can I use it, or where can I find them, and how can I use it, and quickly. Did you find everything? Okay. Any disagreement about these two problems in addition to the problem that were originally solved together, which is a mass diagram problem? Let me get some comments here or questions, unless somebody suggests something. Can you, I don't know what's can you, Larry? I don't know. Can you what? Is the 200 feet? Oh, here it is, a question. Is the 200 feet a tangent offset? No, it is a distance as indicated in the problem. It is a distance along the existing tangent. Here it is. He went back along the original tangent with the same bearing. Okay, maybe if you are thinking about, because I have another problem where this distance from here to here, the perpendicular distance is 200 feet. This perpendicular distance here, this is not the perpendicular distance. This is a distance along the tangent. This is why they draw it. If it's perpendicular, this is the solution will be different. And I believe also I have some problems similar to this, because you have to be careful. Your question is valid, and thank you for asking this question, because what distance he is talking about, because little tiny change in the problem, it will change for sure the solution, and it will give you a different answer. Okay, so please look to these three problems when you receive it. And if you have any comment or suggestion, please let me know. Okay, so go ahead, sir. Go ahead, sir. Go ahead.
For those two questions, right? We talk about stations. Okay, for the question 3, the problem number 3, the station is for the tangent line, right? It's along the tangent line. Station 80 plus 00, and then it change to station 78 plus 00, which is moving back 200 feet, right?
That's correct. Along the tangent, that's correct.
Yes, along the tangent. And then the previous problem, the station is
measured horizontally.
Yeah, measured horizontally.
That's right. Correct.
Okay, and
for vertical curves, all stations are measured horizontally. Yes.
Yes, for vertical curves, all the stations measure horizontally, right?
Always, all of that.
Okay.
Yes.
And this one is also vertical curve, isn't it?
No, this horizontal circular curve.
Oh, okay.
A vertical curve does not have a radius. Sure. A vertical curve is a parabolic curve. This equation here, this is parabolic. Here I'm writing it. Parabolic. This curve came from a radius.
Let me clear about it. So
sure.
Any horizontal curve with the station talking about tangent line, right?
The stations along this, okay, it is measured, okay, along, if it's tangent line, station along this, or station along the curve itself. But not measured horizontally. Here, as you can see, I draw a horizontal line. The curve length is the difference between this station and this station measured horizontally. is not measured along the curve. And this is one of the questions in chapter 10, by the way. If you go to chapter 10, you will find this specific question in order to emphasize this, that the difference between horizontal curves and vertical curves. Horizontal curves are circular curves. Vertical curves are parabolic curves, always, okay? The stations along vertical curves are measured horizontally. Stations along horizontal curves measured along the curve. Vertical measured horizontally for vertical curves. You are very welcome. Go over this and try to absorb these two problems, and I will be glad to add any additional clarification about this, because we need to understand, because as I told you, exams are really okay, tricky as far as the way they ask questions, and little tiny misunderstanding of one parameter is going to give you something completely different from what we are talking about. Okay, great. Let us go over the Werner scale, because I need to wrap it and okay. Werner scale is very old method of measuring diameters or measuring lengths, but we are still discussing it. Even everything nowadays digital, but for the sake of the exam, we need to be aware of the Werner scale. So the Werner scale, either a transit or a theodolite or even linear measurement, consists of two things. We have what is known as the mean scale on one side, and we have on the other side is called Werner scale. Here, you'll find another scale here. It's called Werner scale. What is the purpose of the Werner scale? The purpose of the Werner scale is to get the fractions. And instead of relying on engineering interpolation or engineering judgment, they came up with this Werner scale. And one book is it has a picture. I believe I have something similar to it in my books. Maybe this book here by Barry Kavanagh. Every book has one, but just I grab one. Barry Kavanagh. Okay, this is the 8th edition, Surveying with Construction Applications. If I remember correctly, there was a picture at the beginning. This is color. This is why let me see if I can remember where it is. If not, I will, because sometimes it is much easier to explain it, and I will solve it. I will solve the problem. I have 3 problems given in my book, or my books in general. They used to be at the beginning as, or probably all the way to the end. Sometimes, as I told you, I forgot a lot of things, but or I can go to the index and look for a vernier scale, and I will be able to find it. And this is probably what I will do, because okay, let me go very quick, because this color can help. Let me see, is vernier. Sometimes the oh my God, is not even is not in the index. It seems that he removed it completely, maybe. But let me go. I will go to my book and during next season or next meeting, sorry, I can get a lot of pictures for the Vernier scale from different sources, and we can talk about it. But let me double check at the end. Sometimes they have something related to the instrumentation, but no, I will quit. Let us go to my books. My books, I have some. If you look to this book here, the Surveying Practice Exam and Solutions, you will find an exam number 2, I believe, exam number 2. Yeah, here it is. Exam number 2, problems 24, 25, 26, and 27. And let me get a clean copy, because it seems that I use this copy to explain it to somebody. Let's see if I have a clean copy in my second book here. Yep, here it is. So if you have this book with you, Surveying Practice Exams and Solutions, okay, that's good. If not, any book that it has a Vernier scale, I will explain it such that, and even there are some problems. Let me make a copy. Do you have a copy here with you? You don't have a copy of do you have the book with you? Okay, you don't. Let me make a copy very quick. I need to understand this book. And also I will scan it with, send it to you for those who do not have the book with you. Or obviously this is a copy, so probably the picture is not. Okay. So as I said, that the Vernier scale for any instrument, it does have two side of it. One is called the mean scale, and the other one is called the Vernier scale. Here it is. So this is, let's look to the picture A. So this is a Vernier, okay, and this is the mean scale. So this is the mean, this side is the mean scale. For example, here this is 300 degrees. This for a transit. And this is 60. Obviously, the sum must be 360. It depends on the direction. This is a clockwise CW, and the other direction here is CCW, counterclockwise. And on the exam, he has to tell you which direction he's talking about. So, for example, these problems here, one of them clockwise and the other one counterclockwise. So the direction of the reading must be given to you. This must be given. You cannot assume it. Must be given. So if we look to the first question, which is question number 24 in my surveying practice exam book, Said, what is the clockwise reading of figure A? This is a figure A. So clockwise, I will move clockwise because he told me that. This is my zero reference. We get different color here. This is my zero reference. Everything with respect to this. This is my zero reference, where I read. So the clockwise, I have 50, and this is 51, and this is 52, until we have 55, and I have 56, I have 57, I have 58, and this is 59. Do you see that? Try to make it as large as I can. So in the clockwise direction, because he told me that, I am moving in the clockwise. So it is the first number clockwise, the second below is the counterclockwise, as I said. So it is the zero reference here, or the mark, I like to call it. It is 58, and I did not hit the 59 yet. But I passed half of the mark. Okay, if you look closely, between 58 and 59, let me draw a picture here. This is 58 degrees. And this is the 59 degrees. What they did, they put a tick mark here. This is half a degree. Half a degree is 30 minutes. So this is why they call it this 30 minutes, by the way. This, we'll call it the Vernier. We'll call it 30-minute Vernier. They took the 30, which is the smallest number I can read is between here and here. This is 58 degrees and 30 minutes, if I'm here exactly. But my zero reference is not here. My zero reference is here. Do you see that? This is where it says zero here. This arrow here is this one here. So my reading, I am 58 degrees for sure. And I have 30 because already I passed the 30. So I have 30 minutes. And I have something beyond that. I will call it delta. Let me call this delta, which is between this and this. Do you see that? I need this delta right now. In order to avoid or to help us, instead of using the engineering judgment and interpolation, they said that this delta here, or the fraction here, you can get it from the other side, not from the main scale. This is a main scale. Go to the other side, which is a Vernier scale. So I will go to this Vernier scale, and I will move in the same direction. Since I'm doing clockwise, I have to move in the same direction. And they try to find a line on the main scale, aligned or matching a line on the Vernier scale. So I will move it from here. I will move until you see two lines are matching. I know this is a picture, is not the best. So can you tell me which line do you think? What about this line here? Two lines, they are aligned. One line on the Vernier scale and one line on the main scale, they are matching. You matching mean, here it is, let me draw it. I need a line on the Vernier scale, have the same bearing or the same alignment, here it is. So a line on the Vernier and a line on the main, they are matching or have the same bearing or the same line of action. Matching lines. Do you see that? Okay. So again, as a picture, so this I count right now. This is 0, this is 10, and this is 15, 16, and 17. I will add the 17 to it, 17 minute, because this is 30-minute Vernier, 17. And I will add, this is the delta, the one I was talking about. Here it is. This is the delta. So if I add the delta to it, it is 58 and 47 minute, and this is the reading. And I hope that this is the answer that I selected in my book for a problem number 24. Do you see that? So the Vernier scale is helping us to get a precise reading or accurate reading of the fraction that beyond the scale that is shown, beyond the mini scale capability. Mini scale can read, here it is, 58.5. And a little bit. What is this a little bit? I call it delta. How can I get the delta? I will move along the Vernier scale and try to find one line on the mini scale and the one and the line on the Vernier scale. They are lined up. Here it is, lined up. Here it is. I need this line, the red and the black. Here it is, lined up. The same bearing, the same line of action, this angle 180, whatever you like to call it. Okay. We'll call it collinear lines. Collinear. We have collinear and non-collinear. Okay. So this is the 30-minute Vernier scale. This is a third. They took the smallest division on the mini scale and they put it on the Vernier scale. Obviously, when you go to the other one, which is a counterclockwise, so I will use the number here. Let me go to the count. Still, my zero reference still the same. So this is 300. This is a 301. This 302 because I'm moving in this direction. Okay, so and this is 310 degrees. Okay, I will do the same thing. I will for the counterclockwise, which is a figure, still figure A. You will find the following. Here it is. So I am moving in this direction. CCW. I know most of watches nowadays are digital, and I remember I have an engineer ask me, Dr. Mansour, how I know which direction is a clockwise and counterclockwise? I told him very simple. Go to Walmart, buy $5 watch, and it tells you where is a clockwise or counterclockwise. If you, I said that everything digital. I agree with you. Even this Vernier scale, nobody is using it anymore. Okay, everything digital nowadays. Okay, micrometers and calibers, all the measuring instrument digital. But I don't know why they are still asking these questions. I don't know. Something that nobody is using it, but they would like to respect my grandfather and your grandfather. So they said, your grandfather used a Vernier scale and my grandfather used Vernier scale. So we have to honor them. No problem. I have no problem with that. So counterclockwise, no problem. Just to wake you up. So the counterclockwise, I am here. So this is the 60 and this is 300. They should add up to 360 degrees. This is a mark for it. I have another mark here, which is mark and so on. So where is my zero reference here? My zero reference passed. So I am here right now. This is the zero reference. So right now I am 301. This is 301 because I am reading counterclockwise. A plus, again, I will call it delta. From here to here, this I will call this delta, the fraction. So I have 301 degrees. I remember I did not hit. Okay, let's look here. Make sure that. So 301, and I am here 302. Even I did not hit the little tick mark in between. Let me make sure. Here it is. I don't hit 30 seconds yet, because here it is. Let me get it closer as much as I can to show it to you guys. Here it is. So right now, here is a 0 mark. This is 300, 301. This is 301 and 30 seconds. This is 302. I am here right now before the 3. This is 301. I didn't hit half a degree yet. I didn't hit the, so I will move in the same direction this way and try to find a line on the main scale matching a line on the Vernier scale. Can you tell me which line is that? Any line that they are close? What about this line here? It's not bad line. So I will say this is 300 and I will add 12 plus 12 seconds. So this is 301 degrees and 12 seconds. Close enough. Theoretically speaking, by the way, when you add these two numbers, you're supposed to get 360 degrees. You add these two numbers, they must add the 360. There is a little bit of difference. This 47 and this is 12 or 13. So theoretically speaking, 12 or 13, okay? But a 301, so a 301, 12 is the answer that I will select here. Even I know there is a human error of reading here because they are not adding, oops, sorry. They are not adding up to 360 as it should be. But human error or the scale, the picture, this is the way we read. Okay, this is an easy one. What they did with the second one, which is a figure B as in boy, this figure here, which is this figure B here, they make the situation more accurate, where you can get the seconds. Here, this scale you cannot get seconds, you get degrees and minutes only. Here you can get degrees and minutes only using this scale. Here for this one, you can get degrees, minute, and seconds for the second one. And this is why you will find that a problem number 26 and 28, you will find the seconds are showing here. Okay? What they did here, and let me explain this to you also. Try to make it as, this is a scale B as a boy, and you will find the following. First of all, the Vernier is reference here. This is the reference. This is the 0 reference. Here it is. If you look to the main scale, which is this side here, this is the main scale, and the other side is the Vernier scale. What they did, they divide the degrees into 20 minutes. So between, this is, for example, if we go to clockwise, this is 90, this is 91. How many tick marks between 90 and 91? 2 tick marks with the 3 spaces. Each space is what? Is 20 minutes. Is this correct? Because we know a degree is 60 minutes. So each one is 20 minutes. They took the 20-minute Vernier, which is this one here. This is 20 minutes. The Vernier. But between each minute, this is minute number 1. they put a small tick mark between 0 and 1. There is another tick mark. You see this tick mark here? So they took the between 0 and 1. This is the 0. I'm talking about the Werner side right now. And between 1, this is 1 minute. What they did, they put another small tick mark in between. Okay, do you see that? Here it is, between 0 and 1, the big one, okay? There is a small one. This is what? This is 30 seconds, and this is 30 seconds. Because 30 seconds and 30 seconds will give me 60 seconds, which is 1 minute. So they divide the minute into 230 seconds. So the smallest number I can read on this scale, what's the smallest number I can read? 30 seconds. Can I read 15 seconds? No. Can I read 20 seconds? No. Can I read 0? Yes, I can read 0. So this is why if you look to this and look to the number, question number 26. Sorry, my voice is. Can I read 20 seconds? No, it is out. I eliminate answer A. Can I read C? No, it is out. I cannot do 15 seconds. So the process of elimination is very important. A process of elimination. Because you know the smallest number I can read is 30 seconds. So if you give me an answer 20 seconds, how can you get that? You can't. How can you get 15 seconds? No. And the same story here for question number 27. Sometimes they do that, by the way. Sometimes they give you this type of questions in order to test us, to see if we really understand the concept or not. If we understand the concept, that's good news. If we don't understand concept, it's still good news because we still have time. So again, this is also out for the question number 27. So it is multiple of 30 seconds. It could be even, yes, it may be. And I will do the same thing. So for example here, a clockwise reading of the figure B. So I will say the clockwise, here it is. So I have here 91, this 90 and this 91, and my, okay, 91, and I best one tick mark. So it is 91 degrees, and I passed one tick mark. One tick mark is what? Is 20 minute. Here it is, 91, 20 minute. And this is 40 minutes, and this is 92. But I am between the 20 minutes and the 40-minute mark. So a plus delta. The delta. Okay, and let me draw it here. Let me draw this also for this problem number 26. So at least you can see it. Here it is. I have the following. Again, this is a clockwise. CW. Let me make sure that I have it here for you guys. So I have the 90 mark is here, 90 degrees. And I have the 91 is here. 91 is here. And there are two tick marks here. And this is 92 here. Okay. And there are two tick marks here. Okay, small ones. And my zero reference, where my zero reference, already I passed the first one after 91, so my zero reference is here. And this is what I call delta. between here and here, this is called delta. So for sure, I have 91 plus 20, 91 degrees and 20 minutes plus delta. How much is delta? I will do the same thing, the same philosophy. I will move in the same direction, the clockwise. This is 10 minutes, so I will move, try to find a line on the main scale matching a line on the Vernier scale, starting from here in the clockwise direction. So I will go over them and tell me which line. I know this, probably they. Do you think this is a good match? Okay, so this is. Okay. Seven, another line maybe. Any line that may be better match than this? Maybe the one after, probably. So this is 7, and I have 30 seconds. So I will add delta in this case as delta as 7 degrees and 30 seconds. So if you add them up, will give you 91 degrees, 27 and 30 seconds. And probably, obviously, I hope that they will give you much better picture, but you know the concept. This is the way we do it. And for Vernier scale, and I hope this is helping you, my friend, Mr. Lee, okay, or Lee, okay, Lee, okay, much better because, okay, so I hope this is the, and I will ask my staff on Monday to scan these things. Any other questions? Because I'm not feeling well. In fact, I've been. Okay, any other questions related to the surveying in general? Other than, I don't know how soon. Anybody's taking the exam very soon, by the way? Any exam very soon? Okay. So I will scan these things and send it to you. I need to stop here because for some reason I'm not feeling well, but I did all my best to answer all the questions. And I hope that you enjoyed it, the lecture tonight, and communicate with me if there is anything I can do, even if some of you are taking the exam very soon, and if you send me a set of questions and I can squeeze my busy schedule sometime, I will be glad to do that. I will never hesitate to do that. But we need to understand the concept very, very well. Like, for example, the 3 problems that we solved at the beginning of the session, they are really, really a good indication of if we really understand the concept or not. If not, no problem, no problem. We're still okay. At least we can I can set a special session with any of you who wants to or who is going to take the exam very soon, and I will do all my best to help you guys. And let me go because I have only. Okay, so let me here grab something from you. You say that thing. You are very welcome, my friend. You are very welcome. Studying hard, keep working hard, and I wish you the best in the webinar. And